Cool, what is up math fam? So today we'll be doing our first lesson on exponential functions. So we have your matric exam coming up and we need to revise our exponential functions. So today we're going to be talking about the very most basic situation, right? Our mother graphs. These allow us to see what are the different situations that we can have for an exponential function. And they give us the basic idea of how they look, right? Then we're going to talk about the horizontal asymptotes and what that idea is and how would they impact the questions that we need to do. So let's start with how the basic equation of an exponential function looks. And it's going to look like this. Y is equal to b to the power of x, or in function notation, f of x is equal to b to the power of x. So this is the equation of the mother graph, right? In an exam, you'll usually get it in the form like this, right? We'll have some shifts. So the full equation actually looks like this. Sorry about that. F of x is equal to b to the power of x minus p plus q, right? In other words, we could have a shift up or down, which would be q, or we could have a shift to the left or to the right, which would be p, right? But for our mother graphs, we have no shifts. All that we're interested in is how does the graph look for different b values, right? So to answer that question, let's just go ahead and see how this graph looks. So we're thinking about our b values just for this video, or just for this portion of the video at least. We're only going to think about our b values bigger than 1, okay? B values bigger than 1 mean 2, 3, 4, 5, 6. So when we're thinking about our equation, our equation of the exponential function, then we're thinking about the base, right? The base being the number that we're taking to the power of x. All right, so let's just go ahead and draw this graph. So to draw the graph, we're first going to think about the behavior when x is positive. Okay, so let's start with x is equal to 0, then 1, 2, and 3. This is the easiest way to draw a graph, by the way. There's a 1 over there just chilling. Easiest way to draw a graph, just to use the table. And we're going to see what happens when we plug those different x values into our equation using b is equal to 2. So 2 to the power of x over there. All right. So f of 0, when x is 0, this will give us 2 to the power of 0, right? Which is equal to 1. Now what's important about this is quite a special value. You guys can all shout at me at the same time, why is this a special value? And we know this is special because when x is 0, so in other words, when we are over here, wherever the y value is called our y-intercept. Okay, so we are now talking about the y-intercept, right, when x is 0. And what's important to understand over here is it doesn't matter what the value of b is. It doesn't matter, right? It could be 2, it could be 3, it could be 4, 5, 6, 7, 8, a million, right? Anything to the power of 0 is going to be 1. So for our mother graph, right, for our mother graph with no shift to left or right, up or down, and I haven't yet added the other parts of the equation, but for that mother graph, the y-intercept is always going to be 1. So the point will be right over here. Okay? That's important to us because it makes things easy if you ask that question in the exam. Okay, let's go with the second one. F of 1 equals 2 to the power of 1 gives us 2, nice and easy. F of 2 equals 2 to the power of 2, which is 4. And f of 3 is equal to 3 to the power of, my goodness. F of 3 is equal to 2 to the power of 3, which is equal to 8. Okay, so let's go and plot those points and see what is happening When x is 1, y is 2. When x is 2, y is 4. Oh, my y-axis is a little bit small. And when x is 3, y is 8. That won't even fit on this paper, so we know it's all the way up over here somewhere. Okay, so let's just go and draw that portion of the graph at least. And it's going to look something like that. What's important about this is we see that it's curving, right? This graph is curving. Why is it curving? The reason that it's curving is because every time we go a little bit more to the right by 1. So we went from 0 to 1. When we went from 0 to 1, y went from 1 to 2. Okay? It increased only by 1. When we went from 1 to 2, y went from 2 to 4. It increased by 4. When we went from 2 to 3, y went from 4 to 8. It now increases by 4. Okay, so in other words, what's happening is y is getting bigger faster than x is getting bigger. And that's why this graph is curving like this. What it tells us is that the rate of change is increasing with every x value. Okay, so that's why it's not a straight line. It doesn't have a constant gradient. Now, let's go and think about the other side of the graph, right? This portion over here to the left, when x is negative, what happens? Okay, let's go ahead and see x. So we'll go ahead and graph this 2 to the power of x. Sorry guys, my throat is on its worst behavior. And then that splits out a y. So x is -1, -2, -3. We're only going to test those 3 values. Okay, cool. So f of -1 is equal to 2 to the power of -1. So let's stop here and have a look at some grade 9 mathematics. And our goal is now to evaluate 2 to the power of -1. Now, we know from grade 9, from our exponential laws, that something to a negative exponent is the same as saying that thing, right? That thing, that base, 2, to the same exponent except positive, right? So 1 over 2 to the power of 1. In other words, it now becomes the denominator, of a fraction, but the exponent becomes positive. Okay, so that's important. Let's go and evaluate the next one. So f of -2 is equal to 2 to the power of -2. So y was 1 over 2 over here. Okay, so what's happening? Once again, let's have a look. So 2 to the power of -2 is equal to 1 over. So now, once again, the base goes and becomes the denominator and its exponent becomes positive, right? And that's going to spit out 1 over 4. Okay, so what do we notice? Our fractions are getting smaller, right? 1 over 2 is smaller than 1 over 4. A half is smaller than a quarter. Okay, let's go with our next one. F of -3 equals 2 to the power of -3. What's our answer? 1 over 2 to the power of 3 is equal to 1 over 8. All right. If we go and plot those points, let's have a look. So here's our first one, our second one. Okay, my where I put these points needs to change a little bit. So here's -1, here's -2, here's -3. So this is now going to be a quarter and 1/8, which is super small down here. So what's happening is our y values, as x becomes negative, our y values are becoming smaller and smaller and smaller. So this is, right, this is our mother graph, what we call our mother graph, a very uncultured way of talking about math. You'll never hear me say that outside of this lesson. It's very uncultured, but okay. So that's our mother graph, and this is the situation where b is bigger than 1. So in other words, whenever you see the graph looking like this, right, we say that this is increasing. In other words, the y values are getting bigger and bigger as we go from left to right. So left to right, the y values go up, up. They get bigger. This graph is increasing, and that should tell you immediately, boom, boom, boom. When you in your exam, immediately you should be thinking, when you see this graph, okay, b is bigger than 1. Cool. Our second situation, and I was naughty, I didn't draw out the graph beforehand. I should have done that. But our second situation is b is smaller than 1. Right? Actually, strictly speaking, we'd say b is bigger than 0, but smaller than 1. Now this is very, it's a lot of math language, right? To understand, we always go from math to English. So let's go to our English and say, what on earth is this, inequality telling us? And what it's telling us is this. Simple. B is a fraction. Okay? B is a fraction. So now we're going to have our graph looking like this. F of x is equal to, a half to the power of x, or a third to the power of x, or, a quarter to the power of x. All those different things. Okay, let's go ahead and have a look at how this thing actually looks. So let's go sketch our Cartesian plane. There it is. We're going to need our tables for the two scenarios when x is positive and when x is negative. You guys can actually go and do this yourself, and you don't have to watch the rest of the video. Joking, we're still going to talk about asymptotes, but you guys can still do this yourself for exercise. Okay, good. So that's our nice Cartesian plane. Here's our point 0, 1, 2, 3, 1, 2, 3. That should go further up. -1, -2, -3. Okay. So in this case, we're speaking about b smaller than 1. B is in between 0 and 1. B is a fraction. So our x values go here. For this example, we'll think about a half to the power of x. And that's going to spit out some y. This is supposed to be an x. Doesn't look like an x. It's supposed to be an x. Okay, good. So we're going to start with our negative values first. Opposite to what we did last time. So if x is -1, -2, -3, question once again is, how does this graph look? Right? What's its shape? What is it doing? What are the y values doing when x is negative? Okay, so f of, we should actually start with, let's do this a bit differently. So let's say -3, -2, -1. So f of -3 is going to equal what? 1 over 2 to the power of -3. Now, once again, we're going to have to evaluate this, right? 1 over 2 to the power of -3. And to do that, we're going to need to know our exponential laws once again. So we're going to use the same one that we used before. It has a negative exponent, so this is the same as saying 1 over. Now, our base is a half, so the base becomes the denominator, and its exponent becomes positive. Okay? What on earth does this give us, right? So let's go ahead and evaluate this. So 1 over, do you remember from grade 9? When we have our exponent outside of the bracket, we're going to multiply the exponent of everything inside the bracket, provided that there's only times in between. So don't let me tell you the wrong stuff, but in this case, there's only one number. So everything inside the bracket, we're going to multiply the exponent by the exponent on the outside. So this is 1 to the power of 1, 2 to the power of 1. So this becomes 1 to the power of 1 times 3 over 2 to the power of 1 times 3. And that gives us 1 over 1 over 2 to the power of 3. Okay, so you never really actually have to do this whole long analysis. I'm just explaining it once and once only. If you've forgotten how to do this, what you would be doing is typing this on your calculator. What's that going to give us? Right, now we use our fractions. That's 1 divided by 1 over 2 to the power of 3. Now we use our reciprocal law, grade 9 stuff, times 2 to the power of 3. So a numerator and now denominator switch is equal to 1 times 2 to the power of 3 is 2 to the power of 3. Okay, so very long analysis just to give us this answer. In other words, what this tells us is that when b is a fraction and x is negative, we're going to get some nice big answers. That's all that we were looking for. We're going to get big answers. The shortcut is just to look at this and say, okay, here's a fraction inside to a negative exponent. The answer is going to be the denominator to the power of the positive exponent. Okay, only when the numerator is 1. Don't let me tell you this in general, because it's not true in general. Only when the numerator is 1. So this will be 2 to the power of 3, which will give us 8. The second one we're going to evaluate nice and quickly. Okay, is equal to a half to the power of negative 2, which will give us 2 to the power of 2 is equal to 4. F of negative 1 is equal to a half to the power of negative 1, which will give us 2 to the power of 1, which is equal to 2. Okay, so what that tells us is when x is negative 3, let's go graph these points. Y is going to be 8, somewhere up here, super high up. That's a bit not high enough, but it's okay. When x is negative 2, y is going to be 4. This is closer to 3, but it is what it is. See, I'm very inaccurate with my thing. That's why you should go and draw it yourself. Okay, and when x is negative 1, y is going to be 2. Okay, so this is starting to look more like a line. So let me actually go and make this a little bit more accurate. So that I don't teach you guys the wrong things. Okay, that will be up here, and 8 will be super high up over there somewhere. Okay, the y-intercept is still going to be 1. Tell me why. Okay, good. Now let's think about what is happening when x is positive. Okay, so we'll use this once again. That's going to spit out a y. When x is positive, it's going to be 1, 2, 3. F of 1 is going to give us a half to the power of 1, which will give us a half, right? F of 2 is equal to a half to the power of 2, and that's going to be a half times a half. So a half of a half gives us a quarter, and f of 3 is going to be a half to the power of 3, which is a half times a half times a half, which is an eighth. Okay, in other words, when x becomes bigger positive, when x goes more and more and more to the right, y is going to get smaller and smaller and smaller, right? Because a half is smaller than a quarter, which is smaller than an eighth. Okay, so if we plot those points, it's going to look something like this. My goodness, I made the same mistake as I did before. Let's just take these away, and that's going to be 1, 2, 3. Okay, good. So if we look at these graphs, what do we see? Right? The shape changes. One is increasing. When b is smaller than 1, this graph is decreasing. And that's all there is to it, guys. One more thing that's important to note is that when we look at the y values of this mother graph, pay attention to the fact that y never crosses this line over here. It never crosses the x-axis, right? It gets super close to the x-axis, but it never crosses it. And that's the same for b bigger than 1 and b smaller than 1. So what do we call a line that the function, the y values of the function get super close to, but they never actually touch? What's our special math name for that? Okay, the reason that we need to know the name is because the name is asked in the question. So we always need to think about how do the English and the math, where do they meet, right? So this line, we just go and we call it the, okay, so that is the wrong place to place my arrow. This line is called the horizontal asymptote, okay? In other words, y gets super close to this line. So the y values of the function get super close to this line, but they never actually touch it. They never actually become 0, right? They just get super close to 0, but they don't ever become 0 or less than 0. Okay, in the next video, we'll go into more detail on these horizontal asymptotes in terms of how to find its equation and what happens when we shift the graph up and down, what happens to that asymptote. But for now, that's the basics, and that is your mother graph.